Hello, this is Philip Myers of PEMY Consulting. Please pause the video and read these disclaimers. Before we begin, this video is for educational purposes only. It's not engineering advice and it isn't intended to be used for any specific tank or facility. Always consult qualified professionals and applicable regulations. If you wade through this video to the end, there is information about how to obtain an authoritative white paper on tank shell thickness calculations for tank inspectors and engineers. I recommend you try out these problems included before looking at the answers to see if you are up to speed on your computational skills. I gave one of many presentations at the December 2025 NISTM Tank Conference. This presentation provided a high-level overview of common tank calculation types used to support RAGGEP, recognized and generally accepted good engineering practice. The focus is on how API 650 and API 653 calculations are applied in practice and how they inform engineering, inspection, and operational decisions. There are two commonly used terms in tank and vessel design circles. One of them, design by rule, relies on prescriptive formulas and tables. It's the dominant approach in API 650 and ASME Section 8 Division 1 because it's simple, repeatable, and easy to audit. The trade-off is that it's intentionally conservative. The other term is design by analysis, which can replace prescriptive rules using detailed numerical calculations of stresses and failure modes with tools like finite element analysis software. Design by analysis underlies the basis of ASME Section 8 Division 2 and API 579 Fitness for Service. However, design by analysis requires more expertise and is highly sensitive to modeling assumptions. It's also more difficult to audit and peer review than design by rule methods. API 650 is largely a design by rule built on decades of successful tank performance. API 653, on the other hand, blends design by rule checks, such as for hoop stress thickness requirements, with design by analysis evaluations such as the strength of a locally pitted shell plate area. API 653 allows the use of API 579 when detailed engineering evaluations or assessments are needed. Each major tank component is evaluated using distinct calculation methods depending on the governing loads, failure modes, and applicable standards. For the same material and application and loading, API 650 uses lower allowable stresses than API 653. In other words, it is more conservative. That's because API 650 is designing for very specific concurrent loading conditions at the time of construction. It also includes substantial safety factors for reliability over time. But once the tank is in service, small reductions in thickness don't suddenly make the tank component unacceptable. API 650's conservatism provides a design margin for normal operation with damage that occurs over many years. On the other hand, API 653 reflects current tank damage conditions and often relies on API 579 to give us a quantitative way to assess remaining strength in life. Shell thickness is often governed by global membrane stresses as opposed to local forces and effects. If a tank shell were to globally yield, the diameter would increase, stresses would rise further, and the stability might be compromised, as you can see from the hoop stress formula. So in this case, API 650 and 653 are written to rigorously prevent global yielding with the possibility of a catastrophic failure. For many small tanks, the calculated hoop stress thickness is quite thin, and API minimum thickness and constructability rules apply rather than global stress limitations. For many small tanks, the required thickness for hoop stress can be substantially less than the minimum thicknesses specified by API 650. These minimum thicknesses are not needed to keep the stresses in check, but rather for things like constructability, fabrication tolerances, welding, handling, and long-term durability. Completing the API 650 or 653 calculations does not mean that the job is finished. Tank design and evaluation sit at the intersection of multiple standards: fire protection, wind and seismic loading, materials, and piping, plus any state or local regulatory requirements. Standards evolve faster than regulations, and that creates friction. In some cases, you're expected to follow an older regulatory reference while you know that the current standards follow current best practices and they are better. Practically speaking, that means engineers often maintain more than one technical justification to stay both compliant and responsible for RAGAGET. I've also put together a short paper with worked examples of API 650 and API 653 shell calculations. It walks through the calculations step by step and shows why shell thickness is often governed by minimum thickness requirements rather than hoop stress. The paper is meant as a learning reference, and you can download it using the post on LinkedIn. I highly recommend tank engineers and inspectors test themselves on these basic calculations. Here are some samples of tank calculations that PEMY routinely does. This is the hotel that the conference was held at. This is the Woodlands Marriott Waterway. This is a poster showing where we taught the Tanks 101 course. This is a picture of the exhibitors hall where it was. This is a picture of me and Tracy Sansom of Storage Terminals Magazine, who is head of content and communication. We are celebrating the recently published article about the new API tank standard API 626 for the inspection of LNG tanks, which is currently in development. If you can't find the article, email me and I will be happy to send it to you. Most important, Merry Christmas and Happy New Year's to you all. Have fun, but be safe. Thank you.